Yang here. Oh, and it looks like Bob is hiding out, Russell's hiding out. They have their screens off, so we won't bug them unless they turn it back on. Okay.
I want to kick this off with a question, if I could.
Yeah, go for it, man.
Just point blank, I didn't understand any of that Searle stuff because it went way over my head. But it sounded intriguing, and apparently they've gotten all kinds of good results. But what caught my attention is the whole temperature thing. Am I right in somehow all this spinny, magnetic-y, whatever-y thing it's doing, that's one side's getting hot and one side's getting cold? Did I hear that right? Okay,
yeah.
I'm seeing a couple of nods. So, if that's the case, I'm just, because I don't really want to do this, but if it would lead to a step in some overall information, I'm toying with the idea now of maybe measuring the front side of one of my propulsion plates thermally and the back side thermally.
Jeremiah, you could talk
Would
about
I
that,
be,
right?
is there any possibility that I would see a thermal difference between the front and the back plates?
Bernie?
You got some?
Yeah. Oh, Bernie's in Canada. That's right.
Right. Look, one benefit of being in Canada.
You got lots of benefits.
The forest fire?
No, that's the Aurora last night.
Oh. Yeah, we don't have those in Florida.
Yeah. No.
You guys want to see some freaking Aurora shots? I got some last night.
Protein, right?
I saw Aurora Borealis in upstate New York in August of 1972, but we're too far south in Central Florida to see any auroras.
Yeah.
Too close to the center of Earth's magnetic field.
Russell,
I took my Nikon out, and I took my.
I'm right next to Orlando. I'm north and east of Orlando and Oviedo.
Yeah, guys, I'm gonna.
You're about 20 minutes away from me.
Well, yeah.
Oh wow, cool. We should get together. We should get together.
Jeremiah.
Cool.
Yeah, if you jump on 415, if you take 46 to 415, then you're 5 minutes away from me.
Oh, cool.
You should come by sometime.
Yeah. Send me a text or whatever. Send me your address somehow in the comments section or whatever, however you like.
I'm not doing that, but Tim, is there any way we can connect the dots on that so I can get his address or some way to text him or something?
My phone number. Yeah, give me a call.
You guys can put it in the chat.
There's the private chat.
Okay, I'll put my phone number in the chat.
Yeah, by the way, Drew, when we Jeremiah was gonna have his hand up to I think he wants to answer your question.
Oh, yeah.
Well, actually, I've got a bit of both. I can address Drew's question first about the thermal differential. So yeah, when you're talking about a system where you have a magnetic field where you have a traveling wave flux, if you think about the basic dynamics of a rotating electromagnetic field motor, basically what Tesla is famous for inventing, his favorite thing that he created, you're dragging around a field flux. And so if you have these magnets on the Searle effect generator that are polarized in such a way that when they rotate around the outside, when these magnets go around the larger cylinder, they're a helix. So their helical fields are acting sort of like a screw pump, like an alchemy style pump. And if you think about what they're doing to any kind of charged particles in the atmosphere, they're effectively pulling them down into that. So they're pulling them down from one direction, from the top and into the bottom, depending on the direction of polarization, or if you rotate them in the opposite direction, you get feasibly, the thing to increase weight and flip the polarity of the heat. I heard one thing in the presentations today that I didn't really understand, and it was the claim that, well, the thing was off and there was no motion of the magnetic field fluxes, that there was some kind of thermal differential. And that to me does not make sense, because there should have to be required motion in order to pump any kind of physical amount of MHD or otherwise associated effects. Without a moving magnetic field, you have no way to couple with it. It's like trying to generate eddy currents by just placing a magnet on top of something and then leaving it in place. It's not going to work. So I didn't quite get that, but your thermal differential can be generated by a variety of different mechanisms. You can even use by consideration the patents on ionic cooling or ionic heating, where you can use ions in certain environmental conditions. Usually it's pulled in partial vacuum, never complete vacuum, and you can transfer very high temperatures directly to the surface of a material and heat it almost instantly. You can also cool down materials along the conveyor belt just by hitting them with positive ions, which the electrons are the responsible carriers for the thermodynamic motion. So they actually carry the heat. It's the electrons that will transfer heat from one place to the other. So if you take electrons off of one surface, that surface will get cooler because the electrons are stealing the momentum from the vibration of the Brownian motion in the metals. And the highest energy electrons get thrown off first. They're the ones that you have cold cathode emission from. Then, of course, if you have a positive charge, well, the positive charge is going to rip the electrons off the surface, because positive charges can't just flow as raw protons, but they're going to be ions because you're going to have the electrons in the valence shell. So those will allow you to actually add heat to something. There are multiple mechanisms for ionic or high voltage heating when you have a moving magnetic field to pump the charges. But what I actually wanted to ask, and my question was mainly for Curtis. So I wanted to show you this. It's a very nice unit, and let me pop a flashlight here. So Todd Desiato had this and another one just like it designed. These are basically very large Mach effect thrusters, and they're heavy. Big, thick copper base, very nicely assembled. Total of 12 pass-through bolt holes, only 6 are being used. And my question for you was about the termination to these discs. Now, he specifically ordered the ones that Woodward was originally recommending from the same manufacturer. So these are very hard ceramics, but this is a much larger unit in terms of its diameter compared to the ones that you guys are now testing. And I know the whole issue with friction and trying to get the thing to slide freely and not interact with the framework is a problem. And even in the core fundamental concept of the Mach effect, the fact that this device has a frame around it means that there's going to be a Mach effect interaction with the framework itself. And so even that has a major influence, the test fixture itself. But what he used to terminate the electrical contact on these plates was this interesting kind of tape material that you can get. It's a weaved metallic shielding material, and it's just slightly barely magnetic. But I'm wondering, do you think that's sufficient? Do you think that the compressibility is going to be too soft for good transfer of mechanical waves between the aluminum side here and the copper side?
So, so yeah, that's a good question, and I'll give you a hint. A couple things is the material that's used in between the piezoelectric. We've tried copper and brass. We're currently using brass. So, that's important. Also, what material you use to like glue the stack together. And in addition, the reaction mass itself was something where we had to have different reaction mass thicknesses made to find where the thing would resonate for the materials, basically the speed of sound of the material, the brass. So you may have to have more than one of that brass slug to figure out, where. Now the question, that thing, the way we have it in a frame is that whole device can move freely back and forth. And so the other thing I would warn about is those bolts. We were having bolts fail. And so what we use something where the bolts can like move freely. So there are Belleville washers that you can put on there. You can find. But all that being said, what I'm curious about is how you take that big thing and what you're mounting it on. Is it free to move? Because that's one of the keys.
I've always kind of wondered, in the simplest, I always try to think of the stupidest, simplest thing that could be done in terms of a lab experiment. And you could create a complicated framework and all kinds of slide bushings and many things to connect power. And I get the problem with providing power to these things. That's part of the issue, is that you've actually got to get energy into them. And that has to be connected to something. But
right.
Why not just simply hang this from fishing line? And why not just
that was
power supply?
that's funny because that's what we had. We had when it was in air, we had it on basically some fishing line from the ceiling on a frame, and that frame was kind of holding it up, so it was free to kind of move back and forth. But it was still in the frame. It was on the frame, and the frame had
Right,
bearings.
but you had surrounding matter, right? See, here's the thing. In my thinking, the Mach effect is basically an interaction with any distant matter. And so we're talking about the velocity of C propagation to any surrounding distant matter that might be able to affect it via its mass field interaction. And in this case, I want to try and isolate the effect. So when I'm dealing with this and we're looking at motion back and forth, I don't want some heavy block of metal or aluminum or anything else that's around. I don't want it in a test frame where I have a torsion arm or a fixture or anything else like that, if I can avoid it. If I had to hang it on the torsion scale, I would probably want to suspend this from the arm of the torsion pendulum and keep it away from the physical arm itself, because again, that's more mass, and I would want to try and isolate out all the nearest mass, because again, it's the inverse square of your distance from that mass, and I know that it's contributing. So like if I were to say build a framework of lead, and I were to say this framework is not oscillating, meaning it's not part of the mechanically vibrating circuit, so it doesn't matter how much crap you stick on it. I imagine it could affect the results just because the physical mass is different, not just because the acceleration weight is different, but because there's a different interaction due to the fact that there's more mass. I mean, that is the base principle of the Mach effect. So I would want to get rid of all of that if possible. And I'm wondering if you guys thought about that.
Yeah, so the like I said, the trick is when you get the thing vibrating, and balancing it and how you're going to mount it. So that's why I had that question for you. So you might just put something where it's allows for, like, let's say a speaker, right? If you think about a speaker and you have that element the inside that can move, yeah, there you go. So you can take something like that where it's constraining two parts of the drive, and it's free to move back and forth. See, the thing about this is you want it to have kind of a one-dimensional motion. You don't want it torquing around, because it'll do that, right? It'll violently thrash everywhere, right? So you want to constrain that.
Oh wow, really? That's actually seriously important what you just said there. If you're seeing that this thing has a tendency to twist or torque or do anything else when it should be generating only a linear displacement, what that tells me is that you have a noticeable and probably verifiable contribution from the presence of your asymmetric frame being more mass on one side than the other, which I would likely suspect is the production source of your torque.
Well, yeah, that's right. And the thing is, but you need the different masses to get the Mach effect to happen, right? So in our experiment, we have devices that, and we just made these where, okay, so we're trying to do a verifiable physics experiment that someone can replicate. So we have devices with the piezo stack, a brass mass, an aluminum mass in the frame, and you can take out and take out the brass mass and aluminum mass and put a set of brass masses that are equal in weight with that same stack, and show you can do the same experiment with the same stack, basically only changing one factor, the symmetry of the masses, and that shows when you run that, the Mach effect goes away. You don't get the same push. Okay, so if it was an electromagnetic effect, it was something else going on, that null experiment would not work. It would still push, right? If it was
right,
and some kind of
I understand the delivery time.
That's
right.
The
delivery time of the wave that travels through the back mass, when it actually travels through this mass, it's got to come back through here, and then it's got to bounce back to the other side, and that is going to be transferred through the hardness of these very rigid piezo discs, specifically why they need to be such a hard material and so firmly bonded to each other, right? And then this mass has to reflect that back at a quarter wave, so you get the phase interaction at exactly 1/4 wave apart in terms of the mechanical oscillation, producing your net force, which is that W waveform that Guy Desiato pointed out in his warp drive papers early on. So it's the same one that you guys got. It's what Woodward was really talking about. It's this very idealized waveform that is asymmetric in terms of its distribution in motion over time.
right? And that waveform, that acceleration that the discs are undergoing, so in the piezo stack, needs to be timed with the power in and power out, because in the Mach, the derivation is the change in mass is proportional to that dp/dt. Okay, and so you're trying to basically push against the heavy mass when you're heavier, or and then push against the light mass when you're lighter, just depending on which direction you're trying to go, right? So you can actually get forces in either direction, depending on what signal you're putting in, and the timing. So the mechanical Q factor, and how that whole thing is vibrating. So if you could figure out, there is nothing that says you have to put it in a frame like we have it. That's just kind of a where as found for me.
I see the
joined
difference
project.
actually in Woodward's opinion, where he's coming from and how I think this thing works. And I guess the difference would be he's trying to consider producing the actual force against the reaction mass. And what I'm considering is the reaction mass is necessary to generate the phonon acoustic oscillation to produce the force within the piezoelectric elements themselves. So in my model, the force is produced in the transducers, and in his model, the force is produced with the transducers against the reaction mass.
Yeah. So in his model, what's happening is the mass there's a difference in mass with the piezo stack, because the piezo stack is expanding and contracting, so it's pushing against both masses. And so if it pushes against both masses, and you have both masses of equal mass, and you're timing that correctly,
no displacement
you get no displacement. But if one is lighter than the other, you'll get a reaction force. And
right. By the time the waveform reaches halfway through the big mass, it's already hit the front of the front mass and bounced back to the beginning point. So effectively, that part of the push is done on the front. The push is still happening on the back, though.
So your push, and that's why the frequencies and characterizing your specific drive is important, because that push needs to be the electromagnetic energy you're putting in for the piezo stack, which determines how fast it's needs to be timed with the mechanical properties of both that reaction mass and the aluminum plate. So you're entirely correct. You have to take into account the speed of sound and the bulk mechanical properties of those materials when you're designing this drive.
All that makes sense.
That plays into it.
And then I do have one more sort of impromptu thing just to show off a little bit here, because it's something that I'm working on, and it brings back to Brendo's original opening presentation, where he talked about Sarfati's drive just a little bit. In Sarfati's drive, he's got a parallel plate cylindrical capacitor. He's got a plate on the top, plate on the bottom. It's wrapped around a cylinder. He's got an electromagnetic coil around the outside. And the idea is that you oscillate these things in sync, because you have this electric field gradient that's going to be reduced in between those two sides. And because you have a difference in mass on the two sides, you have a difference in electric field intensity gradient due to the difference in mass. So your electrons are all pulled to one side, right? It's heavier on that side. But then at the same time, you have this torsion, or this twist, which is going to create a differential cross field interaction in space-time. And so through epsilon and mu, you have this possibility of producing an actual force and a physical displacement. So here, there's an interesting thing that somebody built recently. Very nice magnet, by the way, Russell. If you're showing that up, definitely check that thing out.
Yeah, well, that looks like that's a Searle roller, right? So
yeah, that's one of 8 rings that would go on the
Searle rollers are made up of a stack of 8 discs that are joined magnetically, and this is one of those 8 discs.
So, a lot of you guys in the anti-gravity community, you're probably watching most of the channels that exist out there, and let's face it, there are not that many of us. I mean, the numbers are growing, which is really awesome, but we're still sort of a small, tight-knit grassroots community. So most people, you may have been familiar with Kedium Physics' recent videos on the anti-gravity stuff, and I have some suspicions about the 2 most recent ones, but anyways,
I've seen some debate. Jeremiah, do you want to put up some of the Kedium ones? So I think
I don't know if I don't necessarily want to show them. I don't know if he might have an issue with us showing his videos.
Okay.
It is his original material, and I haven't asked for permission, but I made my own version, and so he kind of assembled this thing. in somewhere near Rwanda in Africa, and it's like he doesn't have the resources that I can just pull all of the garbage cans around here. So very easy stuff, right? And it's a total difference. But I've got to be proud of people for pioneering in situations where they don't have as much access to materials. So what we did is 3D print one. So Simon C and I, which by the way I just want to mention because Simon did such a good job on this thing. He is taking commissions now, so I'll try to get that set up. But just to mention, he designed this based on my very crude drawings. So I drew these up. I'll pull the notebook here. It's based around this simple principle where you have sort of an enclosure. You have a plate with top holes. You've got a grid that holds a thin ionization wire that sort of wraps around it. You have some kind of enclosure or cavity, and then you have an electromagnetic bobbin that's over here. So, and the idea is to synchronize the phase of all of these systems together. So I'll pop this apart. Inside, and this will be difficult to see. I'm going to try to use my flashlight to see if I can illuminate any of these thin little wires. But you see these little notches, and you might just be able to see, if you're looking at a computer, if you're on a cell phone, you won't be able to. Those thin little lines, looks like a spider web. So that's an extremely thin ionizer. At the top here, positive ions will be produced at an extremely high efficiency. And they'll be pumped down towards the bottom, which contains a set of piezoelectric transducers that are pumped out through those two wires here. The basic grid array, they're just glued into place and organized. And then around the outside, of course, you have your coil. Now, altogether, what this does is create a standing wave inside this cavity. And that standing wave has ions that are flowing from the top towards the bottom. And as they travel down to traverse their path, there's an electric field acceleration that's positive on the top, negative on the bottom. And the bottom does not have a collector plate. It actually uses the surfaces, the brass surfaces here of the piezoelectric transducers. And so right at the surface, you have a huge concentration of charged particles, which we oscillate up and down in the vertical plane because of the acoustic sound wave. But at the same time, you also have a circulating magnetic field. And so you will produce cyclotron rotation of the charged particles as they swirl down and swirl back up, being moved up and down by the sound waves. They're going to produce Bremsstrahlung radiation, which will change the refractive index, producing slight exhaust to the side, or you'll get emissions to the side in the EM spectrum in the transverse mode, and you'll get longitudinal mode in the up and down or vertical direction. And together, all these things, they produce a coupling coefficient with our background vacuum through the refractive index. And we could look at Sarfati's model and see, for the same reason, that this is effectively very much like Lazar's canister gravity wave generator. It's very much like Sarfati's capacitor warp drive system. It has in common a lot with many patents, and it's something that I thought was rather clever the way that Kedium put it together, and fingers crossed it's actually a real thing that he's got there. But even if it's not, I like the concept of being able to test with a platform that anybody can 3D print. Like, you guys can just print this. You can pop these piezo transducers in there and glue them down. None of this stuff is hard. The bobbin itself to wind the coil makes it super easy. It's 20 gauge wire. I mean, this is all stuff that anybody could replicate. So that's why I think it's rather interesting as a sort of entry-level project, because it doesn't cost a lot to make. It's a rather simple idea. And yeah, my question would be whether or not these piezo discs are they're going to be powerful enough. The way I'm driving them is using this little circuit here. It's a custom wound matching transformer. It's a 2-to-1 ratio. So I can take 12 volts in and I can step it up to 24 volts directly. But in resonant mode with the piezos, I can get it up to over 120 volts. And so it's driven by this very simple 2 MOSFET circuit using IRFC 44 MOSFETs. And it uses a 4452 MOSFET gate driver to drive this 1-to-1 gate drive transformer, which powers the MOSFET gates. Super simple circuit, really easy to drive, and the great thing is you can hook it up to a function generator and control the frequency exactly. So no need for self-oscillation or tuning circuits or tweaking knobs or anything like that. Just run it where you want it to run. So, but that was my update. I may try something like this as my sound source. That's why I pulled it out, to just kind of show there are other options. Now, this one is stock off the shelf. It's not going to go up to the frequencies that we need, but if we replace the windings on the voice coil and tear down the 30-turn windings and replace them with only 5 turns of a thicker conductor, then we can get that same tweeter to perform at from the 40 to 70 kilohertz range, which is where we really want it to work. So that's what I had to show, just a little update.
Appreciate that, Jeremiah. That was awesome.
I was eating lunch.
Yeah.
It brought me back in and busted with food in my mouth. There we go.
I sort of lurked in Adam's Discord chat and watched this thing being built, and I was like, saw it taking form, and just this little primer is the first time I've really seen it all laid out.
Yeah,
It's
yeah.
Well, no,
Inklings.
I'm really glad to see
today
that.
has been absolutely awesome. So maybe we go until around 6, I guess, tonight, if that's cool, and that's about half an hour from now. And then close
I'll
things
stick around
down.
to answer questions. I mean, I don't know if you wanted to, depending on what you guys think, you could open it up to the public. You could pop a link out there on various channels if people wanted to have sort of an open chat.
I don't know. We've got
bring
a
in.
collection of esoteric experts in here. I think David.
Yeah,
was
that we
doing
do.
his
Maybe you're
camera-
right.
David
And
was
it
doing
all
his camera
goes
with a
back
laser
to the
pointer.
toroid, doesn't it? It circles back to the toroids in that esoteric circle.
And then Bernie was, and Bernie tonight. So tonight you're gonna have more Aurora to get photos of.
I know, right? It's like I can't believe the quality of some of the colors I'm seeing in these pictures I took last night, just like in my backyard.
I got a weird question for you. I have a weird question. I went out last night, so I live right on the edge of Canada, right? So I'm a little bit further south, but I went out and looked, and I was out in Blaine, Birch Bay, White Rock area. I looked up, and I saw what looked like almost marine layer clouds, except they were little strangely
No, that
swirling.
was it. And you had to take your phone out and take pictures of it to actually start
and
seeing
so
how it changes.
long
and it's
exposure.
like,
So
yeah,
I got in the car and I drove. I went out to actually because I grew up out in the country, and so I went out to tribal land out in the country, and I'm like, no one's out here, right? Out in fields, farm
no
fields.
light pollution.
Well, it turns out that all the tribal people will love that area, and so I was dodging pickup trucks out there all night with my camera. But they were they were really cool. So, so out there I saw the colors, but the thing that got me was with the naked eye, it looked white the whole time.
Right? The
Okay, so
majority of the time.
Yeah, that's how it started for me where I'm at. I don't know.
And
if
then
you're too
the
close to
longer
city.
I'd watch, the more I would see like a bit of color come
You've seen
out.
color.
You have to adjust to the light, and after a little while, especially if you're looking at the zenith, it was shimmering. It was crazy. It was like in real time. It was like somebody was shining a flashlight back and forth across the oily surface of some water, except you're under the water looking up, and you realize that the water shimmering is actually the electromagnetic field.
Okay,
and the
so
beams are the
Yeah,
the
right.
radiation.
And I always see the
Yes.
shimmers. It's so wild.
I think light pollution is a part of this then.
It is a bit, and like you're not alone. My mom literally said the exact same thing that you did. She was like, I couldn't see any colors until I looked into the pictures. Like it was all white to her.
Yeah. That was weird. So tonight you're going to get more, and Brendan, you too probably. I mean, anybody who got them last night, supposedly there's more tonight. So
Yeah, I was
which is,
curious
I
about
mean,
the
the
whole
elephant
pinks
in the
in the
room. Are we
pictures, too.
concerned
So
about this?
Tonight I'm
Should
going
we
to
be
take an
concerned?
IR filter, and I'm going to block off my camera to see if it cuts off the pinks, because I'm curious why they're so invisible with the eye, but you can see them very, very clearly on the camera, and I'm going to find out what frequency it's at.
So what I can tell you is
some red with the naked eye last night.
I used 3 cameras. I did test shots with 3 cameras. One of them was my iPhone. I got an iPhone 15. This did the best. And my brother's shooting with an Android, and it was comparable. It was about the same. So I would say compared to that, and I have a really nice Nikon. But the problem with the Nikon is you really have to master the settings to do that.
Nikon, forget about it. Honestly, I'm not gonna. I don't just want to blatantly rip on Nikon because it's not like it's a bad brand for cameras, but Nikon CCDs are extraordinarily good at resolving noise and good lighting conditions. As far as the low light conditions, Fuji is one of the leaders. I mean, you look at Fuji's ISO, and it's like 5 digits or more. I mean, so I've seen 6-digit ISOs on Fuji, and you look at Nikon, and it's like, yeah, good luck.
Yeah.
Good luck in video mode. Get good ISO in photo mode, but forget about the video.
And then the other one that I tried was an Insta360, just because I have that, and that was my action cam, right? And that thing, it did not perform. That did the worst in low light, but that's okay. You know, it wasn't designed for that. So
yeah, this is interesting too. This is one of the things that I did. So I modified this Sony Alpha A300. So this is the CCD you're looking at direct here, and then this is the IR filter.
You took
that
the filter
we popped off of it. So what I can do is, and for tonight, I'm going to take this and just set this to the side for now.
Yeah.
And pop back my telephoto lens on here. And so this way, by modifying it that way, you have to take the whole thing apart. I mean, it's a major pain to remove everything and try not to break the damn thing. But you can pop that out of almost any DSLR camera. They'll all have an IR filter in front of the CCD. And so if you remove that, you get something much closer to a full spectrum camera. So now I can see it into the deep IR and I can see into the UV as well. And I would love to see how this will notice those other spectra.
Yeah, so Jeremiah, let me put this up real quick. I want to riff on what you've been saying. I think I showed this to you last week, but I want to show the rest of the audience. Now, I am not recommending this brand, but I would say maybe check out this website. There are others out there. This is a company called Kolari. What they do, among other things, is they take cameras, just like Jeremiah just showed you. What they do is take cameras and they take off the IR and the UV filters, right? And they different cameras have different ways to do that. But one of the things that most people aren't aware of is most digital cameras can pick up at least a little bit into the IR and a little bit into the UV spectrum. Now, from the factory, they block that because it makes your pictures a little more cloudy, right? Like if you get a lot of UV coming in, your picture will not be as clear. But if you're trying to do experimental photography, that might be handy. So I wanted to show people this. And,
I just want to mention, too, with the UV and the IR problem, this is something that you guys have to consider if you're going to do mods to your camera or even buy one of these. That camera, as stock, if you get that straight off the website, is probably going to be totally set and ready for you to go. The problem is the lenses you'll get. If you use classic telephoto lenses, their coatings are not going to be designed for optimizing light frequencies that are in the IR and the UV. So what you'll notice is if you do pixel data analysis from a single light source that's UV, and you have it right next to another light source that's in the visible range, you're going to see the lens will twist that light and push it off to the side. So you'll have an aura or a ring around where you're normally seeing that light. You have to get special lenses if you want good IR and UV clarity.
Okay.
And some of the deeper wavelengths that the CCD can actually see, well, it turns out that they don't ever get to the CCD itself because the lens is blocked. And the same thing for the UV. There's actually other wavelengths that once you do this modification, they could get straight to the camera, and there's nothing wrong with the camera body, but the lenses aren't suitable. So
that's a good point. The other thing that's worth consideration, I looked at the FLIR one, and that's a plug-in for the iPhone. They got a couple of them, but like the older iPhones, right? You plug it right into the bottom, and the new one, it slings over the top. And what I noticed there was the resolution on those is like way, way, way less. And the reason is because you need larger sensors to get those IR frequencies, right? Because the wavelength is longer. So,
I have one of those FLIR ones, and
okay.
It has two cameras. It has the IR and it has a visible light. And what it'll do is it'll kind of like frame the IR in that, so it kind of looks a little bit better.
So it's kind of a blob inside of a frame, sort of a thing.
Yeah, but it blends it in a good way. Like it makes it a little, unless you're doing like some kind of technical measurement, it's not that big of a deal. But they have two models. One that they have different temperature ranges, so just make sure you get the right temperature range. Well, but that is an actual useful tool because you can take it with you and just pop it on when you need it. And the other thing that's
even in your case, Curtis, you see one piezo transducer that's getting really hot with that FLIR, and you're going to know exactly where your problem is. Like you may have a cracked disc, and you would never ever know.
Yeah, so you could. I mean, there's really good useful things you could use, like electronics. Like you could look at that, find hotspots. But the other thing that's really neat is if somebody's walking, because of the heat of their steps, you can actually follow them from behind and they won't even know. You can see steps. Yeah, it's really cool.
Yeah, don't
So
say that
there's
out
some
loud.
spycraft. There's some
We don't want to give
spycraft
people
for
ideas.
Oh, that's kind of scary cool. I like
You know,
that.
the thing that gets me is, you know, I'm interested in these, like, they're useful for experimental work. A lot of people are trying to photograph UFOs and anomalies and things like that. And, you know, it's to me that there's this general interest of like, okay, the more data we can get, the more that we'll know, right? Now, maybe that doesn't help us. Maybe it's not useful, but it would be interesting to see, okay, you know, I got this UFO up in the sky, it's flying around. If I can get some infrared or UV out of that, what is that going to tell me? Does that make it more real, or, you know, or not? I don't know. It's just,
More
you know,
information, the better. Always, right? More
yeah.
data.
I mean, that's kind of where I'm at, you know. So it is interesting. It's useful, and that was why I put Kalari up. And so Jeremiah, thank you, man, because I think that was really valuable to point that out to people. You know, these things can be converted. You know.
Yeah, it's very cross transferable data. It's just interesting to kind of see these technologies developing and the various problems that we face, because some of this stuff, it's like you get into it and you would never expect to have the kinds of problems that you're going to have in the field. It might be that you're running a Vega reactor and everything is perfect and you've got high vacuum, you pumped it down, but it turns out that you freaking the gasket, you know, your wire is transferring too much heat down to the gasket, and all of a sudden you get a vacuum leak down there and you get a catalytic reaction from it. So all kinds of stuff like that, it pops up and you wouldn't think about it ahead of time, but once you do enough of it, you kind of see, you know, and you can predict, here's where the problems are going to be, how we can relinquish them ahead of time, and that kind of stuff. So it helps. I mean, that's why APEC is here, right? We're here to tell each other how we screwed it up so that we don't make the same mistakes again and again.
So by the way, speaking of cameras, so we in the lab, we're using a high-speed camera that can get like 520 FPS, and it's actually meant for astronomy. You can get one for microscopy, I should say. So they have, it's a Sony chip. It's a standard definition resolution. That was the video I showed. So that one, it's actually the problem with those high-speed cameras is the actual speed of the bus. So USB 3, you know, is the limiting factor. So as things get faster, we'll be able to get higher speed. So I think Sony makes one that can do like 1500 FPS. A sensor that can do 1500 FPS, but you have to hook up like 10 gig wire or 10 gig Ethernet or 25 gig Ethernet to get the speeds. So we're, you know, I don't know if we need to go that fast with it, but yeah, there is something to be said for like the camera technology that some, you know, that's used in astronomy and also used in microscopy, the stuff that can be low light. So in terms of like, I have one of those Sony A7Ss. That is 12 megapixel. It's a low light camera. They now have the 3 or maybe even the 4. I'm not sure, but yeah, it's you know, can do, I don't know, ISO like 1,000,000 or something. I don't know, it's ridiculous. And I also took off there is no we took out the IR filter is gone. There's a kind of a broad filter. So I use it for astronomy with the telescopes to get live views, and it's ridiculously fast. So there is stuff out there that you can buy and put together and track things. That's very, very doable nowadays.
Yeah. No, so the other one that I was playing with was again that Insta360, and the idea behind that, and it's kind of an interesting idea. It's almost like a Swiss Army knife camera, and so I'm going to take that down and see if we can use that with Jared. It's got some pluses and minuses. It captures kind of a sphere of video. It has a couple of fisheye lenses back to back, right? And it stitches them together, and it does seamless stitching. You can't tell where one picture ends and the other starts. So on that end of things, it's good. I'm using that new X4, which is supposedly 8K, but it wraps it around. So in terms of actual photo quality, it's a little bit less than an iPhone, and that's a little bit of a downer. You know, you're doing 360 photos, you're not going to complain about it, but it's definitely not even, you know, iPhone or Android quality. It's a little bit below, but the advantage to it, I guess, or at least our hope is that you might be able to stick this thing in, up next to an experiment or into a chamber or whatever, and you don't really have to know exactly where your photo is going to be. It's going to capture everything, and you can reframe after the fact. So
Yeah.
so we'll see how that goes.
Yeah, I noticed Bob came back and then went away. So
Yeah. Well, I think we got probably about 10 minutes left for today. I want to thank all of you guys for joining us. I mean, it was awesome digging into this, especially Brendan. Thank you, man. You had, again, that was like the off-road challenge for presentations. So
that was tough. I wanted to share some of the shots I got from last night.
Yeah, put them up
on big screen really quick if anybody was interested. And this, bringing it back to the Taurus again, my understanding was not just, so somebody, I think it was Russell, said it's because of the thinness of the electromagnetic field up here. I think it's also because the more of the radioactive particles are brought toward the top and bottom of the Taurus, which is part of the reason why you see the Aurora Borealis in the north, which is, it's all coming back to the 0 point. But
I want to mention to you, Brendan, did you see my post on Space Case's server? I did do checks of the radioactive CME burst rate compared to the average during the solar storm while we were actually getting good photos. And it turns out that the background levels were not any higher than normal, but we got quite a few bursts that had as many as 30 counts per second. So the average level didn't really seem to change. The burst level did increase.
Interesting. Yeah, I don't know what the exact levels are. I'll have to take a look at that. But I saw an image, a visual representation of how much more intense the radiation is right now versus normal background. It was some random example from 2009 or something, but I think we're definitely getting like peak solar activity, but I just wanted to share this.
Hopefully, like,
So many
what
people out
happens
there
if
hopefully
it
we all
gets
stay
more
alive.
intense than this? Like, what if there's still
That's a good
a full
question.
year of escalation? Like,
who knows? And then what does that represent? And the things I was seeing in the sky last night sure looked like the glyphs from the Rongo script in Easter Island, according to Robert Schock. And it's just a little bit concerning. It was like beautiful. I'm like, this might be a harbinger of doom.
Did you have some pictures, Brendan?
Yes. Hold on.
Yeah. As you pull that up, Brendan, I'll just mention to the audience still listening, like, a lot of you have probably been having some pretty crappy sleep lately. It is not you. It is not just you. There are huge studies on this.
But you know what? I want to share with you. I'm the only person with a Y2K prediction that came absolutely true. So far, I predicted when everyone else was doom and gloom, I said, nope, it's going to be another 2,000 years of the same old BS.
I predict we'll get more lights, but we're still going to be able to be here again month after month because the internet won't go down and no doom and gloom.
Those are good. Those are good photos. So it looks like the ambient light looks like you had some problems with that the same way I did. It looks like it washed.
Yeah, these are from earlier. I'm showing these backwards in time, that for some reason, like retro causality or whatever. But yeah, this is earlier in the evening when the light was still lighter. Although so what I experienced when I went out at first was kind of like you, which is like, I thought it was clouds at first, and I wondered if it was Aurora, and it was so. But then I went out, because I go out often, because a lot of my lifestyle is outdoors here on the farm. But I went out like just an hour later, and it was like, whoa, I have to get the kids. Like, it was above me. So it was just really, it was especially intense at the zenith. And that's where you got like these bird-like forms as the rays were coming down in your direction. I think it had a lot to do with it. It seemed like more of the rays were coming from the direction of the ecliptic, is what it seemed like. And that's what made the unique forms toward the ecliptic, which is here where I am at.
You saw a lot more red than I did. I saw more green.
And the pictures don't do it justice, because they were all moving, and it was shimmering in real time like a fish You know, it was
right. The
really
shimmer
intense.
is just
The
so
shimmer got me.
wild how it happens, and then
It looked like
when
somebody
they
was shining a
focus
spotlight
together-
around. Yeah, it was.
Yeah.
It was
And
nuts.
I tried getting
Very
video,
cosmic
but
experience.
none of my cameras would pick it up on video.
Right? No video. I got you, Tim. It just
No,
goes
wouldn't do
dark. It
video.
doesn't capture it at all.
Yeah.
You have to go in the pro settings. Like pretty much every Android has them, but you have to go in the pro settings of your camera and turn on long exposure. Most of these were 30 seconds at least, so I'd let it sit.
So,
there.
by the way, for the iPhone, there's an app called Nightcap Pro, which actually is a stacking program that'll actually stack images. So you can do low light stuff. The only thing is, it has to be absolutely still. So you'll want it on a tripod or in a stand or something. But yeah, that's something that you can kind of almost turn your iPhone into a kind of like a low level astrophotography type of camera.
That's good
Cool.
advice.
And to be honest, it requires less
This is what it started
configuration than
as.
a
This is the
regular
beginning.
camera. So
Yeah.
This is the baseline. This is Aurora. This is the baseline. This is Aurora. Like
yeah,
that's what it looked like
get
at
some good
first,
photos.
beginning of the night.
I couldn't believe it, Brandon, but even in the washed out light and all of the street lamps and everything in Milwaukee, Wisconsin, we were still able to see it with the naked eye, but we did not see the reds. We had to use our cameras to see the reds.
Lots of purples.
Yeah,
Yeah.
yours are intense and very detailed. You got a lot
So-
more of the fine
So
detail.
you have apparently you'll have another opportunity tonight. So I guess we'll give it a try.
Right, this is just from my little Samsung camera. No overexposure or anything.
Hey, you know what? Again, the smartphone cameras seem like they do better, and I think it's because they require less expertise.
Exactly, right? They just work.
Yeah,
Maybe,
I could not get anything in real
Maybe
time.
Mark and
whatsoever.
Michael will be able to actually see these things tonight. You know, it would be a shame if you didn't get to see it because he's a Skywatcher too.
Yeah.
It
Well,
was
guys, we got probably about 6 minutes left. So if you have anything to wrap up,
I was wondering if Bob is there. I just had a couple questions for him if he's still there, but I want to see him on the.
yeah. Well, I
see if he
think
shows up.
we're probably just about there then. So why don't I do that? So why don't I close things down for this evening? I think that we've just kind of it sounds like everybody's going to be going out trying to get more Aurora photos. At least everybody who's far enough north, and and then the folks in Florida can benefit from our late nights, hopefully. So.
and I recommend going out around 10 to midnight wherever you are, and
Yeah.
just looking and taking at least a few minutes to let your eyes adjust, take photos up, and then majority of the time what you think are clouds are actually clouds of ionized gas showing beautiful colors in the skies above.
Well, guys, let me close things down for today. It has been APEC for Saturday, May 11th, 2024. And I want to thank everybody for joining us and have a wonderful weekend.
And if anyone afterwards has anything to discuss, please do stick around just a bit after we end this.